Let's find an operational amplifier like, and I know one that is really nice to model, which is the OPA211 of Texas Instruments. And we do the download datasheet. So let's say from this operational amplifier we want to make a small signal dynamic model. So we want to make a model that we can use for evaluating the small signal dynamic behavior of our circuit later. So requirements for those performance aspects related to that will be done in the next lecture. So here we are just going to model it without asking ourselves, is this what we need, yes or no? So here are some features of the operational amplifier, but that is more for our selling than for our technical stuff. Here is the noise, but we want to do the small signal dynamic behavior. Now maybe I can make this a little bit, combine it with my wonderful writing tool you see here. So what we want is we want to make a small signal equivalent model of this thing, and that will consist of something like an input impedance. Usually it's a resistance and a capacitance. Common mode impedances, so let's do this plus and minus input. Common mode is usually modeled by capacitor, so it's going to the ground node. Well, and the ground node is the same as the one of the output nodes in this case. And then a voltage controlled voltage source. So this voltage is the voltage that we are going to measure. And we have a voltage controlled voltage source. This has a gain AV, so plus minus AV times VI, grounded here, and an output impedance here, and this is then our output terminal with respect to ground. So ground plus minus and output, that is what we have. Let's see what we can make of it. If we can find numbers and we want to make a model for this having poles and zeros, and here a model having a DC resistance and poles and zeros, etc. So can we make this model of this amplifier? Let's go and scroll through the operational amplifier datasheet and see what we have. And there is like, here is maximum ratings, blah, 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 thermal conditions, electrical characteristics. This is all about DC, offset, bias. This is not what we need. Input impedance. You see, input impedance differential mode is 20 kilo ohm and APF. So that's simple. That's just, we know, we just fill it in our thing here. So what did I say? 20 kilo and APF. Common mode, you see this is 10 giga ohm. Well, okay, I can put it in if you want, and then we have to put here resistor of 20 giga ohm and here, because together they are then 10 giga ohm. But let's not worry about it. 10 giga ohm is so large that usually it plays no role in your circuit. And 2 PF, so I do 1 PF here and 1 PF there. You might say, if I measure the common mode or the differential mode input impedance now with a floating measurement instrument, I would measure 8 plus 2 times 1 PF in series.
Anton, I can't see your figure.
Oh, sorry. Good thing. I have to go. Okay, so thank you, Chris. You might say that if you want to measure the differential mode input impedance and the input capacitance now, that you measure 8 PF, this one, in parallel with 2 times 1 PF in series, which is 8.5 PF. So you could say, subtract that one from 8 PF and make this one 7.5, and then it's okay. That is depending on how the thing is defined. Let's just keep it this way and go to the voltage gain. The voltage gain. And now there is something interesting about specification of operational amplifiers. They call the voltage gain the open loop voltage gain. Unfortunately, loop is not a property of the op-amp. So it should just be voltage gain. And this is very confusing, talking about open loop when there's no loop. This is the gain of the operational amplifier. So, and you see, it changes a little bit. If I have 10 kilo ohm load, it is between 114 and 130 dB. If I have 600 ohm, it is between 110 and 114 dB. So let's take the typical values. And remember, 120 dB is 1 million, and 10 dB is the square root of 10, is about 3.16. So this is 3 million. The DC gain is 3 million and drops to 1,500,000. This is 500,000 if you would put it in a linear scale. So it drops when I'm going to load my amplifier. That tells me something about the DC value of this resistor, of this impedance. Because here I have, let's say, 3 times 10 to the power of 6, and then I have poles and zeros. I don't know yet. And this impedance must be such that if I connect here 600 ohm, that it drops from 3 million to what I said, 500,000. And if you calculate that, I think I remember the value, but don't blame me if it is not correct. Then I'll say RO equals 8 kilo ohm. So you find it from these numbers. And unfortunately, it's not always specified this way, but this I took here an operational amplifier that has this specification. So we have numbers to determine the DC value of the small signal output impedance. Then it says it has a gain bandwidth product of 80 megahertz when the gain is 100, and of 45 megahertz when the gain is unity. Let's find a plot. Let's see if we can find a plot. A plot of both a plot of the transfer of this operational amplifier. And there must be something here. We have a power supply reaction ratio, blah, 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 blah. Here. Go on mode. Did I skip it already? I think I was already passing it. Gain and phase versus frequency. That's this one. You see? Here is the pole. And here you see what happens here. It looks like it's not an order of going from -1 to -2. It's like more complex. And you see the phase here. The phase, well, here is clearly the phase is going to 90 degrees because it's an integrator. And they measure inverting input. That should, of course, be 0 degrees and then -90. But okay, that is, you have to really always study what they mean with these numbers, because of course for DC there's no phase shift, so it should be 0. But if you measure the inverting input, it will be 180 degrees, of course. So we go from 0 to -90 degrees. Then there's probably a second pole, and then something happens, and you see like there's a 0 coming, and here is another pole coming. So that is, but the phase, if the 0 is coming, it would go to -180 degrees. So 0, -90, -180, but this is not happening. So here's a lot of more small stuff happening. And we can try to estimate this from this figure. And that's why we did all these exercises to find relation between pole zero diagram and the magnitude and phase plot of a transfer function. So let's try to do this. And here we have the output impedance. That's seldomly specified. But now you see, they plotted from 10 Hertz. It appears to be like this. But where does it stop? Can anyone tell me the character of this output impedance? Is it like resistive, inductive, or capacitive? Can you put an answer on the chat? I don't see any answer yet, so just do something. What you think is the matter here? Is the output impedance a resistor in this region? A resistor, a capacitor, or an inductor? Well, I'm glad I see a lot of good answers coming. It's capacitive. It's capacitive. And now the question is, how large is this capacitor? Well, you just take a frequency and say, well, it's 20 ohm at 1 kilohertz. You see, 20 ohm at 1 kilohertz. So we have a capacitor C. So we have the resistor already, but it must be in parallel with the capacitor. And this is C equals 1 over 2 pi 20 times 1K, because it was 20 ohm at 1 kilohertz. And if you do that, I have my calculator here. If you don't believe me, I have to see, that's my calculator. You will find 7.95, let's say 8 microfarad. So this is 8 microfarad. And of course, no one put 8 microfarad in there. And this was 8 kilo ohm. Of course, no one put 8 microfarads in there because but this capacitor is a result of all, let's say, frequency compensation techniques that are applied in the operational amplifiers. For those who are interested, you will find something like a schematic. They have it somewhere in this data sheet here. And you see all kind of frequency compensating elements generating, in fact, a kind of high capacitance output character. So that's what we are measuring there. But it's not capacitive for all frequencies. Here, it stops. And here, well, what is happening here? Is it capacitive, inductive, resistive? Put it on the chat again. Inductive, I see. Okay, here we have inductive. Indeed. So we have inductive, and we can see, let's say it is like 10 ohm at, well, 1.8 megahertz or so. So I think so. And if you calculate it, I think it was like a few hundred nanohenries. Let's put it, I don't want to do the calculation, but let's say just 700 nanohenry. I think it was, if I remember well, because I did it before. But if we would have, oh, you want to see my result, of course. If we would have, so I put that 700 nanohenry, if we have this capacitive character abruptly changing to 700 nanohenry, then you would find a characteristic like this. Here is 8 microfarad. So this is frequency, and this is magnitude. And here you have 700 nanohenries. And here you have the resonance frequency. So this is not happening. What is happening is that it stops at about, well, a little bit below 1 ohm. You see, 0.7 ohm or so. So that's not so difficult. You find from this a nice start value for this resistor, which is 0.7 ohm. Of course, it should be in parallel because it limits the impedance of, no, sorry, it should not be in parallel. This one should be in series. Of course, it should be in series. I'm glad your teacher can make errors of 0.7 ohm. Because it doesn't limit this behavior. This is still inductive. It limits this behavior. And what happens here? Here it stops at about, let's say 70 ohms. So this is a resistor in parallel, and here it becomes capacitive again. So you can calculate from this the capacitor again, and then we have a complete model of the output impedance. So it would be, let's draw it again, but not in a little bit more clean way. So we have 8K, 8 micro, 0.7 ohm, 700 nano, and this was, I said 70, isn't it? 70 ohm. So this is now our output impedance if I don't account for the last capacitive behavior, because that is at very high frequency and might not be of interest. But if you want, you can add it and go on for higher frequencies. Is this procedure clear to everyone? How this works? And this is luxurious because it's seldom specified like this. So here we can have poles and zeros, one pole, and here a second pole and a zero, something like here. And then you, of course, it's not a perfect model, but you have a correct model up till, let's say, maybe 50 megahertz or so. Okay, that is the modeling of the dynamic behavior of the operational amplifier from a data sheet as an example, and you can try this yourself. And there are in the SlideCap library you find the complete model for this OPA 2.11. Maybe I can show you the SlideCap library. We have a few minutes left for this. SlideCap lib, SlideCap.lib.
Question in the chat, Anton.
Yeah, I will do it. I will do it. I'll finish this one and then we'll do the question in the chat. So. Here we have the OPA 211, differential mode, 8PF. Input conductance, it was 20K, so it's 50 microsiemens. The common mode capacitance was 2PF. And the voltage gain here is the expression with the poles and zeros, and the output impedance is here. You see the 0.7 ohm in series, and so it's like, and this was 3.6K. Oh, it was, I took 8K, it was 3.6K. Okay, and 8 microfarad. So this is what SlideCap requires, and now we have a model of this operational amplifier, which is good enough. We don't need the whole macro model. This is just describing the dynamic behavior, small signal dynamic behavior. If you want to make an application of this operational amplifier, and the bandwidth of this application, let's say the bandwidth of the amplifier that you are making should be in the order of 10 megahertz, then of course your model should at least be good up to 10 megahertz. But we will find out in the next chapter, the next lecture, that non-dominant poles can have a significant influence on stability. And so usually you want to be, and that's just a rough rule of thumb, you want to model 10 times more than the bandwidth than you need. So if I want to make a model of this amplifier for, let's say, if I want to make an application for 10 megahertz, then I would like to have a model up to 100 megahertz. But that is not it's a rule of thumb, and it's really difficult, but because let's say the capacitive behavior, if you have a capacitive load of this amplifier, it can be very important where this capacitor, if I put a capacitive load here, so this is my load characteristic, then here I would have resonance. If I put the capacitive load here, a very small capacitor, so high impedance, then you see it is not influencing anything. If I put it here, well, then I can usually use only this model, or if it is a very large capacitor. So in this range, a capacitive load is looking like dangerous if I only consider the output impedance. So it's not simple to answer. Usually take 10 times more than the bandwidth than you need, but it really depends on the specific situation with your load impedance as well.